Hey there, everybody. Welcome back. We got done talking about the limits for 13.2. We're doing limits and continuity for multivariable functions in Calculus 3. We talked about limits in the other two videos for this section, including delta epsilon proofs. Let's talk about continuity. So for f of x, when we say f of xy is continuous, there's not going to be any jumps. Like there's no changes in values, there's no tears like an absolute or an asymptote or anything like that in there, where there's a whole line that's bad. There's no holes where there's just like you can't have it at 0 or something like that. So f of xy is continuous if we're doing the limit as xy approaches x naught y naught of f of xy, that we get f of x naught y naught every time for all x naught y naught, at least in some region R. And we'll say region R or domain R. If that's true, then f of xy is continuous everywhere. And like we had with, we were working with just single variable functions. If the functions are individually continuous, then any arithmetic combination of them or composition of them works as well. But you just keep in mind that if the denominator goes to 0, then it has a problem. So division can be tricky, but addition, subtraction, a product of two functions that are continuous results in a continuous function. Compositions of functions are continuous if the original functions are continuous. Just pay attention when you do division. We don't want the denominator to equal 0. That results in f of xy being undefined. Some things that are always continuous: polynomial functions. Polynomial functions of two variables are continuous in two space, which is written as R2 like that. The R means real space. So let's just take a look at an example. The limit is xy goes to 2, 1 of this long function of f of xy. X to the 4th y minus 2x cubed y squared plus 3x squared y cubed plus 5x minus 6xy plus 7y. Each of these are polynomials. If we look at them individually, x to the 4th, the y, they're all continuous. So the product of them, the addition of them is continuous, which means we can just plug in 2y and get the limit. So we just evaluated f of 2, 1, not 2y, 2, 1. We just evaluate our function at 2, 1 by plugging those in. I didn't do that here. That's just some tedious math right now. If we take a look at f of xy equaling x squared minus y squared over x squared plus y squared, I labeled the top a and the bottom b. Those two functions are individually continuous. But since we're dividing, we have to pay attention for problems in the bottom. And the only time there's a problem on the bottom is if it equals 0, and that can only occur at 0, 0. So we have to take note of that. It's not, there's a discontinuity at 0, 0 because it's not continuous there. Sometimes what they do to address this is they will say f of xy equals x squared minus y squared over x squared plus y squared if x squared plus y squared does not equal 0, i.e. x does not equal 0 and y does not equal 0. And then they'll say f of xy equals, what would the top equal if we had it? X squared minus y would be 0. We could make it continuous if we set this equal to 0 right there, if x equals 0 and y equals 0. So sometimes they will do that to do this, to address a hole. This is called, when they do this, it's called a removable discontinuity. Like it was discontinuous, but they addressed it. Let's take a look at another example. We're going to have g of xy is equal to sine of x squared plus y squared over x squared plus y squared. We want to take the limit of it as it goes to the origin. And we know the bottom equals 0, but the top equals 0 too. So an easy way to do this is we can parameterize. We can make x squared plus y squared equal t. And now we're just saying t is greater than or equal to 0. T can't be negative, which means we've got a one-side limit. We're only addressing t is from 0 positive. And now we'll say the limit of gt as t goes to 0 positive, which is the limit as t goes to 0 positive from sine of t over t. Use L'Hopital's, you get cosine t over 1, and we know that limit is 1. When we evaluate at t equals 0, we can evaluate that. Therefore, the limit is xy goes to 0, 0 of g of xy equals 1. Through that, if you want to do the delta epsilon proof, go right ahead. It's a pain in the butt trying to even do the delta. You kind of have to start with the delta epsilon proof of this. And most arguments to show that this equals 1 are done geometrically. It's not pretty. I'm not going to waste your time with it. Let's take a look at another one. Something else. We've got f of x equals x cubed. G of y equals 8y to the 4th. We'll say h of z equals cosine of z. All of those functions individually are continuous. So we can look at the composition of them. We could say z equals f of x times g of y, which would make it 8x cubed y to the 4th. And that would make h a function of x and y. Thus, h of x and y is cosine of 8x cubed y to the 4th. And since all of those individual functions were continuous, this is continuous as well. One last little tasty tidbit. What happens if you got something crazy like the limit is y approaches the origin, where our function is x times y over the square root of x squared plus y squared. What do we get for the limit? We get zeros on top, zeros on bottom. How do we do the L'Hopital here? It's a little tricky here. We could try polar though. So switch to polar. And so like here, r is equal to x, the square root of x squared plus y squared. And that's a distance. And that's, so as that goes to 0, as the origin goes to 0, the radius is going to 0. And again, radius has to be positive. So we got to do r0 from the positive side. We look at the limit as r approaches 0 from the positive side. X is r cosine theta, y is r sine theta. And then we got the square root of x squared plus y squared is the square root of r squared. We know this is positive. We don't need absolute values. One of the r's will cancel, and we've got r cosine theta sine theta. And as r is going to 0, the limit of this is going to 0, which means the limit of the big boy is going to 0, the x and y function. It's all kind of fun. Something we'll need in the next section. It talks about open sets versus closed sets. So I've got some region here, R, that I've got shaded in like lightly in red. And we call a set open if everything inside of it is just interior points. And then if we, so that's my A picture here. I have all the interior points. I don't have anything along the boundary of R. The boundary of R is that curved line B. And since the boundary of R, since B, if I use that as my set, it includes everything inside and the boundary. It's called the closed set of R. It contains all boundary points in R. And when we have something like C, where we got some of the values are in R in a region and some of the values within that little curve are not, we say it's neither open nor closed. We will use the idea of closed set and stuff like that in the next section, 13.3. Peace.